Picture 3,000 stone structures scattered across 6 continents, built by people who, as far as we know, never met, never traded, and never spoke the same language. Now imagine feeding every coordinate, every alignment, every AI analyzed every ancient megalithic site, and found a pattern historians missed. Measurement of those structures into an artificial intelligence and asking it one simple question. Is there a pattern here that humans have missed? That is exactly the kind of experiment researchers have begun running, and the early results are forcing some uncomfortable conversations in archaeology. Before we go further, here's a promise. This video will not feed you a tidy conspiracy. It will walk through what megalithic sites actually are, what large-scale data analysis can and cannot tell us about them, and where the line between genuine mystery and wishful storytelling actually sits. Stick around, because the truth here is stranger than the myths, just not in the way you might expect. Let's start with the word itself. Megalithic simply means made of great stones. It's a catch-all term archaeologists use for structures built from massive, often unworked or roughly worked stone blocks, frequently without mortar, sometimes weighing many tons apiece. The category includes famous giants like the Great Pyramid of Giza and Stonehenge, but also thousands of less famous dolmens, standing stones, burial mounds, and temple platforms scattered from Korea to Ireland to the highlands of Peru. What makes them fascinating isn't just their size. It's that megalithic building traditions popped up again and again, in places with no obvious connection, across a span of more than 10,000 years. Take Göbekli Tepe in southeastern Turkey. Excavations there revealed circular enclosures with T-shaped limestone pillars, some carved with foxes, boars, and birds, dated to roughly 9,600 BCE, thousands of years before agriculture became widespread in the region. That date alone overturned an old assumption in archaeology, the idea that monumental architecture required settled farming communities first. Göbekli Tepe suggests hunter-gatherers organized large cooperative building projects before they had domesticated wheat. That's not speculation, it's a documented shift in mainstream archaeological thinking. And it happened because the evidence forced it, not because anyone wanted a dramatic headline. Compare that to Stonehenge, built in stages starting around 3000 BCE, where blue stones were hauled roughly 150 miles from the Preseli Hills in Wales. How Neolithic builders moved stones that size that far is still debated, with theories ranging from sledges and rollers on greased timber tracks to partial water transport along rivers and coastline. Experiments by archaeologists have shown that with enough manpower, rope, and clever use of pivoting and timber cradles, you don't need lost technology to move multi-ton stones, just patience, organization, and a lot of people willing to pull together for a shared purpose, probably religious or ceremonial. Then there's Machu Picchu, built by the Inca in the 15th century, where granite blocks were shaped and fitted so precisely that some joints really do resist a knife blade. Inca masons used techniques like pecking and grinding stone surfaces against each other until they matched almost perfectly, a slow, labor-intensive process documented in colonial-era accounts and replicated by modern experimental archaeologists. It's not evidence of vanished super technology. It's evidence of an enormous amount of skilled labor and generations of accumulated stoneworking knowledge. So if all these sites have ordinary, if impressive explanations on their own, why would anyone bother running them through an AI looking for hidden connections? Because pattern recognition across huge datasets is something computers are genuinely good at, and archaeology has historically struggled to analyze global datasets at scale. A single archaeologist might spend a career studying one site or one region in incredible depth. Almost nobody has the time to personally cross-reference the precise GPS coordinates, construction dates, and astronomical alignments of 3,000 sites worldwide. That's exactly the kind of large-scale correlation hunting that machine learning is suited for, and it's why some researchers have started experimenting with feeding archaeological databases into statistical and AI models, not to prove ancient civilizations were secretly connected, but to see if there are overlooked regional patterns worth investigating further. Here's where we need to be careful, though, because this is exactly the point where good methodology and bad methodology start to diverge sharply. If you take any sufficiently large set of points scattered across a sphere, like the Earth, and you're willing to search through enough possible groupings, you will always find some subset of points that appear to line up along a great circle, an astronomical alignment, or a numerological ratio. This is a well-known statistical trap called the multiple comparisons problem, sometimes nicknamed Texas sharpshooter reasoning, after the joke about someone firing a shotgun at a barn wall and then painting a target around the tightest cluster of holes. With 3,000 sites and dozens of variables, an algorithm without strict statistical controls will almost always discover some eye-catching alignment purely by chance, simply because there are so many possible lines, dates, and ratios to test. That's the core problem with viral claims like these 5 sites fall on one great circle with less than 1 degree of error, or this pyramid encodes pi to several decimal places. Researchers in geodesy and statistics have shown repeatedly that with 3 or more points and a flexible enough definition of alignment, you can draw a great circle through almost any combination of major landmarks on Earth, the same way you could draw a straight line through almost any 3 cities on a map if you're allowed to choose your start and end points after the fact. The pyramid and pi claim has a similar issue. The Great Pyramid's base perimeter divided by height does produce a number close to 2 pi, but this emerges naturally from the sect, a simple slope ratio that ancient Egyptian builders are independently documented to have used for constructing stable pyramid angles. You don't need hidden mathematical sophistication to explain it. You need to know how Egyptian architects actually built slopes, which we do know from their own surviving texts and tomb illustrations. The Orion correlation theory, the idea that the 3 Giza pyramids mirrored the 3 stars of Orion's belt as they appeared around 10,500 BCE, deserves a similar dose of caution. This idea was popularized in the 1990s and remains a favorite of alternative history media, but professional Egyptologists and archaeoastronomers have pointed out multiple problems with it, including that the supposed offset between the pyramids and the belt stars doesn't match nearly as precisely as proponents claim, and that the pyramids were built and dated through a well-documented combination of inscriptions, pottery sequences, and radiocarbon analysis of organic material in the mortar, which places their construction firmly around 2600 to 2500 BCE, not in some unrecorded prehistoric epoch. A theory being widely shared online doesn't make it data. It makes it a popular story. None of this means there's nothing real or interesting going on when researchers look at megalithic sites with fresh analytical tools. There genuinely are open questions in archaeology about regional cultural transmission, about how building techniques spread along trade and migration routes, and about why certain construction methods, like dry stone polygonal masonry, show up independently in places like Peru, Greece, and parts of the Mediterranean. Mainstream researchers do study this through comparative analysis of tool marks, quarry techniques, and the physical properties of local stone. The honest current explanation in most cases is convergent technological development, meaning that when different cultures face the same basic engineering problem, like stacking heavy stone without mortar in earthquake-prone regions, they tend to arrive at broadly similar solutions, because there are only so many physically stable ways to balance large rocks on top of each other. That's not a mysterious, shared inheritance. It's physics being physics everywhere on the planet. The same way unrelated cultures all independently discovered that round wheels work better than square ones. Acoustic resonance in certain chambers, like the King's Chamber in the Great Pyramid or some Neolithic tombs in Ireland, is also a real and measurable phenomenon, studied by actual acoustic archaeologists. Stone chambers of certain proportions naturally produce resonant frequencies, the same way an empty bathroom produces echo and reverb that your living room doesn't. Whether ancient builders deliberately engineered these effects for ritual chanting, or whether the acoustic properties are simply a byproduct of building enclosed stone spaces of a certain size, is a genuinely open and actively researched question, and it's a far more honest mystery than claims about lost supercivilizations. So where does that leave the idea of an AI sifting through global megalithic data? It leaves it as a tool with real potential, but one that needs to be handled the way any serious scientific instrument is handled, with controls, peer review, and skepticism toward results that seem too clean. A well-designed study might use machine learning to flag genuinely unusual clusters of similar construction techniques across regions with documented or plausible trade contact, helping archaeologists prioritize which sites deserve closer comparative study. It might help model how building techniques diffused along known ancient trade networks, like the maritime routes connecting the Mediterranean, or the long-distance exchange networks across the Andes. That kind of work is valuable, incremental, and exactly the sort of pattern detection AI is well suited for. What it almost certainly will not do, and what no credible peer-reviewed study has ever actually demonstrated, is reveal a single lost global civilization that taught every megalith builder on Earth the same secret mathematics from a forgotten golden age before the end of the last ice age. That hypothesis, often called the lost civilization theory, has been floating around for over a century, gaining new energy every time a documentary or best-selling book repackages it. It's a compelling story, partly because it taps into a very human desire for our ancestors to have been more mysterious, more advanced, and more connected than the historical record currently shows. But compelling isn't the same as evidenced. The actual archaeological, genetic, and geological record, built from radiocarbon dating, sediment cores, ice cores, ancient DNA, and tens of thousands of excavated sites across every inhabited continent, simply doesn't show a single advanced predecessor culture wiped out around 10,800 BCE. What it does show is something almost as remarkable in its own right, that scattered groups of hunter-gatherers and early farmers, working independently with nothing but stone tools, rope, timber, and an enormous amount of organized human labor, were capable of engineering feats that still impress us today, without needing help from a vanished super-civilization to explain it. That's really the heart of why megalithic sites deserve our attention and our awe, just not the kind dressed up in pseudo-scientific certainty. The real story is that ordinary humans, with ordinary tools but extraordinary persistence, cooperation, and accumulated generational knowledge, built things that still stand thousands of years later. The real mystery isn't some hidden global code waiting to be cracked by an algorithm. It's how exactly a community of a few thousand people on a remote Pacific island managed the logistics of carving and moving nearly 900 multi-ton statues, a question current researchers are actually closing in on through experimental archaeology involving rocking and walking the statues upright using ropes, a technique demonstrated successfully in field tests. It's exactly how Inca masons achieved such tight-fitting joints without metal tools, a question being answered piece by piece through careful study of surviving quarry sites and tool marks. These are real, ongoing, fundamentally exciting areas of research, and they don't need exaggerated claims to be interesting. If artificial intelligence ends up playing a genuine role in archaeology's future, and there's good reason to think it will, it's far more likely to look like satellite imagery analysis, revealing buried structures invisible from the ground, like the thousands of previously unknown Maya structures uncovered through LiDAR scanning of the Guatemalan jungle in recent years, or pattern recognition helping sort pottery styles across thousands of excavated fragments faster than any human team could manage. That's the unglamorous, genuinely transformative version of AI in archaeology, quietly accelerating real discoveries rather than manufacturing dramatic ones. So the next time you see a headline claiming an AI cracked the secret code of the ancients, hiding in plain sight for 10,000 years, it's worth pausing and asking a few simple questions. Was this published in a peer-reviewed archaeological or statistical journal, or only in a video description and a blog post? Did the researchers control for the fact that with thousands of points on a sphere, alignments, and the appearance of 1 in 40 million probability statements are easy to manufacture after the fact? And does the explanation require us to throw out radiocarbon dating, geology, and genetics, 3 independent and well-corroborated lines of evidence, or does it work within them? Extraordinary claims still require extraordinary evidence, and so far, the genuinely extraordinary thing about humanity's megalithic past isn't a hidden global conspiracy of forgotten knowledge. It's that people just like us, separated by oceans and millennia, kept looking up at the same sky, working with the same stubborn stone, and solving the same hard problems on their own again and again, leaving behind monuments that still leave us in awe today for entirely human reasons.